Okay, I hope everybody can see it. Okay, sorry. So again, connection matrix is a way of summarizing a vector field. And recently, there have been some tools called multi-vector field, which discretizes a vector field and which allows us to apply persistence-like algorithm, which I'll be talking about today. Now, maybe many of you are familiar with Foreman vector field. So, okay, so let me skip over this. So here is a vector field, a cartoon picture of a continuous vector field where I'm showing the flow lines, some of the subset of the flow lines. Typically, it looks like this. But we cannot work on this one because this is not discretized. So there is a discrete notion of a vector field where I'll be defining the vector field on a cell complex. To me, I choose simplicial complex to define the vector field. And how do we define that? It looks like this. So a vector in this combinatorial vector field is a collection of simplices. That's it, nothing else. It's a collection of simplices with certain condition. The condition is this collection has to be convex in terms of the phase-poset relation. Okay, so most likely the definition I'm going to give you, the multi-vector field, is a generalization of Foreman vector field. Okay, what is the definition? Definition is this one. Suppose I have a simplicial complex K, and a multi-vector V is a subset of K. Okay, with the condition it is convex, meaning that if sigma and tau is in the vector, then all simplices in between with respect to the phase-poset relation has to be in the vector. That's the only condition. Okay, so in picture you can see in this case, suppose this vertex and this triangle is in the vector, then this condition tells me that I have to have this edge and this edge also in the vector. And that's the notation of these arrows. And Foreman vector field is only defined with tuples or singleton. Okay, but here we allow any number of simplices to be in a vector. So that's the multi-vector. Okay, so suppose we have this multi-vector field. Then, sorry, a multi-vector. Then a multi-vector field is a partition of K into multi-vectors. That's the simple, it's a very simple definition. And because of this simplicity, you can work with it very nicely with algorithms. Okay. Now, let me define a dynamics. Remember, in a vector field, always the dynamics is very important, means the flow lines. So how do you define it? The definition is given by this concept of paths. So the dynamic FV takes a simplex sigma. Where does it take? Either it takes to any simplex to which it belongs to, the vector it belongs to, or it can take it to any of its face. So for example, I can go from this edge to this triangle because they are in the same vector, or I can go from this edge to vertices because they are in the face. This is the only way you can move from one simplex to the other. And a path is a sequence of simplices satisfying these conditions. Okay, so and this path actually defines or mimics the flow. Now I'm going to define what is the concept of Morse set. The Morse set, actually, you should look into it as the generalization of the critical points or even the orbits. Within the vector field, there are orbits, which are something like generalization of critical sets. Okay, so Morse sets actually, what I'm going to define mimics this critically in some sense. So a Morse set is given by a set M, such that every path, sigma 1 through sigma n, if its two endpoints are in M, then the entire path has to be in M. So basically, from the Morse set, once you go out, you cannot come back. That's the definition of the Morse set. You can see the simplicity of the definitions allows us to play with it. Okay, that's the definition now. So here is a cartoon vector field and its Morse decomposition. What is the Morse decomposition? Morse decomposition is the partition of K, the intersimplicial complex, into Morse sets. Okay, and what happens is that this Morse sets, this decomposition, I can index through a partial order or a partial poset P. Okay, how? the partial order on this index set P is given by P less than equal to Q, if and only if there is a path from MP to MQ. MP is the Morse. So if you can go from the Morse set indexed at P to a Morse set indexed at Q, P is less than equal to Q. And that defines always a partial order. There is no cycles. Okay, so for example, here is a very simple vector field. Vector field consists of this vector, the vertex and edge, vertex and edge, vertex and edge, vertex and edge, this singleton, the edge, the green edge, the singleton, two triangles. There are how many Morse sets? There are one. The two triangles, they become the repellers. They repel. Then this edge becomes the saddle because flow comes here, goes here. So that's the saddle. That's the third Morse set. And then this entire, this collection of all these vectors together make one Morse set. That's the orbit. So I have four Morse sets, and this is this depiction of the partial order. You can go from this triangle to the saddle to this orbit. Similarly, from this triangle. And of course, from the saddle, you can go to the orbit. Once you are in the orbit, you are trapped. You cannot go anywhere else. Okay, so this is the depiction of the Morse decomposition indexed with the partial order, the poset.
So maybe a dumb question. You're not demanding it's a full vector field. Not everything has to get an orientation. Just the, like in this example, just the edges.
Actually, there is no orientation. It's only a subset of simplices. For our intuition, I have drawn those arrows. Okay. There is no actual arrows because it's only a subset of simplices. Okay. So now, how can you compute a Morse decomposition? We, in computer science, we know how to compute strongly connected components in a directed graph. There are efficient algorithms for that. And that's how you just compute the Morse decomposition given a multi-vector field. Because you just compute for every simplex where it can go, put an arrow. For example, the triangle ABC, I can go to A, I can go to AB because of the face relation. But for example, the vertex A, it can go to AB because of the vector relation. Okay, so put those arrows, it becomes a directed graph, compute the strongly connected component that gives you all the Morse sets. And also it gives you the partial order, the entire graph which I showed you on the right. Okay, that's a very simple computation once you know how to compute the strongly connected component. Now let me define what is called an exit set. The exit set, as the name says, basically for a Morse set, exit set encompasses the portion through which you can exit the Morse set. Remember, for a Morse set, once you exit, you cannot come back. And combinatorially, what it means, you take the closure of the Morse set, take the Morse set out of it, whatever is left, that's your exit set. So for example, the exit set for here, for this edge, will be nothing but the two vertices. Because these two vertices are not in the Morse set of this edge, but they are in the closure of the edge. For example, those triangles which are in the pink, their exit set will consist of this edge, this part, and all these edges and vertices, because through which it can exit. From this pink part, you can exit to anywhere here. Yeah, so and on the left-hand side, I'm just showing the continuous part so that you can relate the discrete to continuous. There is a very nice correspondence between continuous description and the discrete description. Okay, so that's the exit set. Now the Connolly index is defined, it's a very simple definition. Connolly index is nothing but is the relative homology of the, again, I'll be talking about under Z2 everything because it becomes easier for me. So it's the homology, relative homology of the Morse set relative to its exit set. So for example, for this two-dimensional thing, the pink set, what is its relative homology? It has only relative homology is H2. Because remember, this exit set is the entire boundary. Relative to the boundary, it just gives you an H2, nothing else. Similarly, for this edge, the saddle, the Conley index is only in H1 because relative to these endpoints, it becomes an H1. What is similarly for this one is H2. What is the Conley index for the orbit? There is nothing to relative to. Relative part is empty. So in this case, it has H0 definitely and H1. Okay, these are the Conley indices of the Morse sets. Okay, that's the definition of the Conley indices of the Morse set. Okay, now the definition of connection matrix. Is a definition probably is a little difficult to give within a few minutes, but I'll just tell you, algebraically it is defined as the boundary homomorphism from this Conley indices, direct sum of Conley indices over all P's or over all Morse sets to itself. Okay, and how this boundary homomorphism is defined? It is defined by the parity of the chain homotopic path which connects MP to MQ. So between two Morse sets, from MP to MQ, how many paths are there? Take the parity of that because I'm operating under Z2. Okay, the parity is with respect to the chain homotopy. That's a little bit not so easy concept, but you can translate everything in combinatorial terms. Okay, and the beauty of our algorithm, all these definitions are for definition's sake. Algorithm just takes care of it. You don't have to do anything explicitly with homotopy and all this. Okay, so and I'll show you. So basically, connection matrix is this matrix representation of this boundary homomorphism, which I'm showing on the right. Okay, this will be clear in a moment, probably much better once I go. Okay, so here is another depiction of connection matrix, which is called the Conley complex. The connection matrix, in a sense, is the boundary operator of the Conley complex. Okay, what is the Conley complex? So, in a sense, the Conley complex actually summarizes the entire vector field into very few cells. It's a cell complex such that the boundary, so for example, let me show you, this triangle here is represented by this cell. And from this cell, the flow goes to this edge and also to this orbit. Okay, the entire orbit has been squeezed to one cycle with a pinch point. Okay, and then this one is also squeezed to this point. So that's what this loop. And within this loop, this triangle is squeezed to this two-dimensional face, and this one is squeezed to this two-dimensional face. So that's the Conley complex, and you can see the connection matrix is nothing but that, in some sense, is the boundary operator of this Conley complex. So this really summarizes a huge vector field, which could be represented by lots of simplices to a very few simplices. That's why it's a summarization of the vector field, which summarizes the flow, the connection between the different Morse sets. So how to compute this connection matrix from the original description was the problem. Okay. And there was not many people who looked into it, at least from a combinatorial viewpoint. There was only one algorithm which was known by Harkar, Mischayko, and Spenlove. But the algorithm was quite complicated, and its complexity was higher. But they first noticed the connection between persistence and connection matrices. But our algorithm is much more simple, direct, and I'll show you the algorithm, and you'll see what is the connection between persistence algorithm. We have to modify persistence algorithm quite a bit to get to the persistence, to get to the connection matrix. What you can do. Okay, here is another example just to show. Here is a vector field, again, combinatorial vector field on the top. There are three vector fields and their simplification. That one is nothing but a repeller and the orbit. That one is nothing but a repeller, but this repeller has something in it. It's like almost like a torus. It's a pinch torus. Okay, so that's why I have to introduce this one. So this cell, the edge, the two vertices, and of course, this loop. That summarizes this one. Okay, and that completely summarized by a single dot, because everything goes to this blue triangle is an attractor, nothing else is happening. Okay, so the summarization of that one will be in the connection matrix, it's a single cell, 1 by 1 matrix. This one will be 5 by 5 matrix. This one will be maybe 3 by 3 matrix. So you see from the boundary operator, which can be huge, thousands of simplices, but you can bring it down to few simplices, which summarizes the entire vector. And that's the power of connection matrix. And we can compute it efficiently. Okay, so now let me go to the computation. How do you do it? First, what do you do? You compute the Morse sets, as I told you, using this strongly connected component. Then put those Morse sets in a linear or so we have this partial order P, O set P. I can always have a linear order out of this partial order. Any arbitrary linear order is fine, as long as it respects the partial order. Do that and use that order to arrange the Morse sets in your matrix. So for example, in this example, I have put the repeller here, the last Morse set. The next one is here. Then the saddle is CA, is here. And then the orbit is entire Morse set is here. So there are these 4 Morse sets. Okay. Within a Morse set, you have to order the simplices as we do in persistence. All faces should come before the simplex. That's the only condition. So again, this is very important. This order is one thing which is very important, which is different from persistence algorithm. Here you take the order of the partial order given by the Morse decomposition. Okay, so that's the first thing. Second thing is, I'm going to define a column in a matrix, a homogeneous column. What is a homogeneous column? A column in a matrix is a homogeneous column as long as its lowest entry is given by a simplex or the row corresponding simplex. Like for example, AB, the A, its lowest simplex is by B, and this simplex should be in the same Morse set. Then I call this column to be homogeneous column. Okay, for example, this is not a homogeneous column because its lowest entry is given by CA. CA is not in the same Morse set as CDA. So that's not a homogeneous column. But this column is a homogeneous column. Right now, this is also a homogeneous column because C is already in the Morse set. Okay, and a column is called a targetable column if it is the lowest entry of a homogeneous column. So there are these 2 concepts. One is homogeneous column, which also gives the notion of targetable column. Okay, what I'll do, the algorithm will use this concept of homogeneous column for reductions. Okay, let's see. Okay, I can skip over this one. This is just to illustrate the persistence algorithm, but you all know how persistence algorithm work on matrix. So again, so the algorithm will work from left to right, as in the persistence algorithm. But here is the difference. The conflicts, like in the persistence algorithm, the lowest one conflicts with anyone to the left if another column has the lowest one at the same row. But this time, the conflict only happens if it is triggered by a homogeneous column, not by anybody. So conflicts with homogeneous columns only, that's one thing. So if a column has the lowest row with the lowest one with a homogeneous column, that's the conflict. Otherwise, it's not a conflict. That's the one difference. Second difference is the conflicts can happen from both left and right. In persistence algorithm, we always do from the left, but this time it can happen from both left and right. And the third difference is that you resolve the conflict not only at the lowest one, but at all entries. That's the third difference. And the fourth difference is how do you output, when you are done with the reduction, how do you output from this matrix a connection matrix? You only output all those columns which are non-homogeneous and non-targetable. And that's it. That is guaranteed to be a connection matrix. I'm not going through the proof. Proof is really quite nice and beautiful. It's in the paper. And but all these things, the magic works. Okay, so let me illustrate how the algorithm is working with this example here. So for example, here, when I reach at AB, nothing happens because there is no conflict, nothing. So AB I pass. The first time I have a conflict, probably in the column BC. In the column BC, is lowest one conflicts with CA, but CA is not a homogeneous column, so nothing happens to BC. But at the entry here, at the row B, I have a conflict with the column AB. Remember, at all entries, I have to consider the conflict. Okay, so then I will add AB to BC. So if you add AB to BC, what happens? Let me annotate. So this one will be go out, and I will have a 1 here when I add. But then BC, it does not conflict with anybody. I'm done with BC. Okay, next I come to CD. Now CD has a conflict with the DA, the column DA on the right. Okay, because these are homogeneous columns. So then I'll have to do this addition from DA to CD. So if I do that, this one will be the case in CD. But now CD also conflicts with BC to the left. So I add, and this entire column CD is zeroed out now. Okay, so let me show you. This is what will happen after you do that. Okay, so CD is zeroed out, DA is this. Now I'm done with this Morse set at this stage. Now I come to CA, the column CA is in a different Morse set, remember? And now CA conflicts with BC. That is allowed because BC is a homogeneous column. So I have to resolve it. So BC will be added to CA. And if you do that, CA is zeroed out. Okay, so ultimately what you will get after doing this reduction, nothing, the CA will be zeroed out, but ABC, nothing happens. Because nobody is in conflict, nothing happens for CDA. You can check. Okay, so we are done with the reduction at this stage. Now, how do you output? As I said, the output is only the non-targetable and non-homogeneous columns. So let's look at it. In this example, why I'm outputting only those columns? Because first, the leftmost column, A, definitely has to be output. Is non-homogeneous, non-targetable. Nobody has targeted. Okay, and that corresponds to this vertex, actually. Okay, and then comes this orbit. The orbit is given by the column CD. CD is zeroed out, is non-homogeneous, and it is not targeted by anyone. You can check. So CD, yes.
What was targeted? That is complex.
Yes. Targeted is after you have reduced whoever is the lowest one in a homogeneous column, corresponding to that simplex, that column is target column.
Okay. Okay.
So in this case, BC, yes. For example, BC, the column BC, in this case, C is a target of BC.
Right.
So because if I did not have this notion, I would have output C. But now I will not output C because it's a target already. So I will not output that. Okay, so this is the column for this cycle, which is given by CD. And then, of course, the CA is not non-target, and it's also zeroed out, non-homogeneous. That is output. And then these two triangles. And you retain only the ones, whichever is given. But for example, ABC has 1 here at CA, I have a CA. For this one, CDA, I have 2 ones. And you can see this mimics exactly this one because the purple triangle has 2 boundaries. Like there are 2, so it can go here and it can go here. Okay, but this triangle, it only goes to this one. Okay, you can see it was also going to the orbit, but that is already mimicked because you can go from here to the vertex, which is mimicking that you can go to the orbit also. And that's it. That's the algorithm. But you can see this is the algorithm which you can now implement very easily. And here is my fresh PhD student, Andrew. Andrew is implementing this algorithm. He has already implemented this algorithm, but we are trying to scale it now. Okay, and it's very simple. You have a vector field with a combinatorial vector field. You compute this Morse set up this matrix, do this reduction, done. You get the summarization of the vector field. Okay, I believe this will be very useful because to track it, suppose you have been given an arbitrary vector field, by looking at it, it's very difficult what is happening. Like the one I show you at least on the top, one of the examples. But once you see this summarization, oh, this is only a single vertex or only two, three things. All right. One thing, there is no unique connection matrix. There could be more than one connection matrix. So for example, for the same example, I have two connection matrices, and you can see the difference. Either you take the pink one outside or the purple one outside. That gives you the two different connection matrices. So in general, it may not be unique, but anyone is equally good. I think I am done. Thank you. And this is the paper actually which has been accepted in the Science Journal of Applied Dynamical Systems. It's also available in the PPT. Thank you.
So the vector field you mentioned here is basically like a vector defined on the manifold, and the algorithm somehow connects to the or relate to the connections, so like a Civi-Levita connection, right? Something like that.
Yes, but maybe you are saying.
I mean, Levita, right? Yeah.
I do not know whether it is okay. The connection from the differential geometry to this one,
exactly.
Yeah, Levi-Civita is in the differential geometry. So I do not know exactly what is the connection here with exactly, but maybe they are related. But one thing is, how do you get from a real data set to this setting? Real data set, most likely you can sample at the vertices. You take a grid, sample, but from this sampling at the vertices, you can go to a multi-vector field. There is a easy algorithm how to do that. That one step you do, that can convert the basically combinatorial. Yes, somebody else? Yes.
Thank you. That's very interesting. For the reduction, since we need to go basically, if I understood correctly, if you have a column that you can basically on a uniform, then the pivot, you need to remove that pivot from any other element in that row. Yes. So do you do the exhaustive reduction, or is it useful to have the exhaustive reduction? So let me tell you, there is an efficient version of it also. Okay. And we are. And he has implemented the efficient version. It's working. We are working on the proof now. Okay. So very frankly speaking, only left reduction should be enough. Right. Okay. Yeah. But the reason, so in the exhaustive method, what you do is once you find a pivot, you zero out the rest of the column, the rest of the row, to save off the operation later. Oh, so we don't do it right now. Oh, okay. Okay. Just. Yeah, you could have done that. All sorts. That is another thing. All sorts of optimizations we have found in the persistent algorithm. How to translate it here? That's another thing. We have not looked into it. But that's a good question.
Maybe one more, but then we probably need to go to the next one.
Yeah, this is really great stuff. So after the persistence algorithm, we read off certain things from the matrix, and I mean, people who study these things, they're interested in the dynamics, like Marian Rosick and Konstantin Shaiko. So can you like read off like invariant sets and various things from from this?
Well, how to interpret the from the connection matrix, how to get the invariant set? Yes, that's another issue. Means one needs to look into it. But the Morse sets themselves already get it. The Morse sets are the invariant sets. Oh, by the way, there is a different Morse decomposition, but we take the minimum Morse decomposition, the finest Morse decomposition. Because, for example, the entire complex is a Morse decomposition. Yeah, but you take the finest decomposition. So that's okay.
All right, probably we should transition you up to Graben later.
Thank you.
Okay.